Justin Miller, Oxford College of Physics here. We are still looking at some traveling waves on strings. And what we want to look at this point is some ideas about the energy involved with traveling waves on a string. So what do we have? So we've got these waves are being produced, right? Something has to be providing the energy. That energy that is provided gets transmitted as this wave continuously travels across the string. So there's energy involved with this, right? What types of energy? Well, we got kinetic energy for sure. We think about these individual mass elements. What are they doing? They're going to be moving up and down and up and down. Sometimes they're at turning points where the velocities are zero. Sometimes they're at the equilibrium position where their velocity is a maximum. But every element across this string is merely moving up and down like little simple harmonic oscillators. So the individual elements have kinetic energy, which is going to be 1/2 times the mass element multiplied by its transverse velocity squared. So we've got kinetic energy. We've also got potential energy as well. We go back and think about the simple harmonic oscillator. We had potential energy that was ultimately a consequence of the spring being compressed or stretched by a certain amount, the 1/2 kx squared, right? We've got the same sort of thing here. All these little mass elements obey like, or act like little harmonic oscillators because they're restoring. There's a restoring force acting on them due to the tension in the string. And as they go away from the equilibrium position, we have equilibrium like across here, y is equal to 0. As they move away from it, there's a restoring force that's trying to push them back down. But it depends. Is it going up and slowing down? Is it going down and speeding up? That kind of depends, right? But there's a restoring force, and it behaves very, very similarly to that of a simple harmonic oscillator, mass spring system, if you will. So what do we have? Well, we've got energies. And what we want to do is look at the energy of a traveling wave. So, energy associated with a traveling wave on a string. We have kinetic energy with mass elements of this string. Moving up and down. Having transverse velocities. And we also have potential energy associated with the restoring force of this string, associated with the string. So this is what we've got going on. We've got those two types of energy. Let's look at kinetic energy. It's a little bit easier to deal with that because we know the form of kinetic energy. Potential energy, we'll make some direct correlations and kind of extract that out. So let us consider kinetic energy of a mass element dm. So we just take some little mass element here, infinitesimal, says dm. Yeah, the string has some overall total mass, and these are just mass elements, infinitesimal mass elements. So what would the kinetic energy be? Well, it would really be a kinetic energy element. So we would have dKe would be equal to, well, 1/2 multiplied by the mass element, dm, times the speed of that mass element squared. Well, the speed is the transverse velocity quantity squared. So there would be the kinetic energy element of an individual mass element. Fantastic. Well, all the mass elements ultimately do the same thing, right? They oscillate up and down, and up and down, and up and down. So what can we do with this? Well, we can start to think about integrating and adding up the contribution of the mass elements. How many of them? To what end? Well, if we did one complete cycle, we'd have the idea of how much energy there is in one full wavelength of the wave. And that's meaningful, right? Because that correlates with how long the string is and all sorts of things that we can do with that. So typically what we want to do is talk about the kinetic energy of one cycle. The kinetic energy of one full cycle, lambda, is then, what do we have? We've got Ke is going to be the integral of dKe, which is going to be equal to the integral of 1/2 dm v sub y squared. And we do this over one wavelength, right? From 0 to lambda. One wavelength. So we could say Ke of a wavelength, kinetic energy of one wavelength. So what can we do with this? Well, we can start to break this apart and note some things about dm. Well, this string has to have some linear mass density. The linear mass density of the string is mu, which is equal to the mass per unit length. That's it. So we've got ourselves that dm can be written as mu dl. This is the length element of the string. Let's say the string is laid across in the x direction. So we can write that dm is equal to a mu dx. Fantastic. We've got that going on. So we've got dm, and we also need ourselves this v. V sub y is the transverse velocity. The transverse velocity of a wave on a string, v sub y, is equal to negative a omega times the cosine of kx minus omega t. There's a plus phi in there, but if you think about it, we're going to go ahead and integrate over one full wavelength. So it doesn't really matter where we start, as long as we do one full wavelength. So the easiest thing to do would just be say that the phase constant doesn't matter, or that it's 0 for that matter. So there is the transverse velocity. So when we go ahead and do this, we've got ourselves that Ke sub lambda is going to be equal to the integral over one wavelength of 1/2 times mu dx multiplied by negative a omega cosine of kx minus omega t quantity squared, 1/2 m v squared. Furthermore, we're not really concerned about time either. We could look at over one complete cycle at any moment in time. Time's really just constant. This is like a snapshot. We just want to know what's the total kinetic energy in one full wavelength of the wave. So let t equal 0, since we just want total energy, the total kinetic energy of one full wavelength. Doesn't matter what time. So let's just let it be equal to 0. That's the easiest thing to do. That term goes away, and what are we left with? We're left with Ke sub lambda is equal to integral from 0 to lambda of 1/2 mu dx a squared omega squared cosine squared of kx. There we go. So there's a bunch of constants in here, right? We got a factor of 1/2. Mu's a constant. We're going to say that that is constant. It has a uniform linear mass density. A is a constant, the amplitude of the oscillations of the wave. Omega is a constant, the angular frequency of the wave. And the only thing that's not constant is x. And that's what we're actually integrating over so that we can add up all of kinetic energies over that full wavelength. So we get to the point where we can write Ke sub lambda is equal to 1/2 mu a squared omega squared multiplied by the integral from 0 to lambda of cosine squared of kx dx. All right, so we've got a cosine squared of kx dx. So we want to integrate that. Well, this is something you can look up, or maybe you recall, or you can figure out by doing some U substitution, stuff like that. Not going to really go through that. All that we need to know is that we could rewrite the cosine of cosine squared of kx as something completely different. And what can we write it as? We can write that the cosine squared of kx is equal to 1/2 plus 1 over 2k times the cosine of 2kx, just kx, is the cosine of 2kx. So, right, and we get a 4k, this doesn't belong here. I believe that's good. 1/2 plus 1/2 the cosine of 2kx. All right, so let's roll with this. Pretty sure that that's good. Anyways, let's see. So now we've got ourselves that Ke is equal to 1/2 multiplied by mu a squared omega squared times the integral from 0 to lambda of, factor out that 1/2 times 1 plus the cosine of 2kx. So what can we do with this? This is a little bit easier. That 1/2 we can put out here, and then we can go ahead and integrate that portion, and we've got that this will be equal to now 1/4 mu a squared omega squared. Again, this 1/2 came out here. Then we've got the integral of 1 dx. So what is that? That's just going to be x. So now we've got x. And then we've got the integral of cosine of 2kx dx. And I think this should have been negative here. Minus, I think that's what I messed up. I get mixed up on that. It ends up not mattering. I'll come back and make sure. But anyways, what do we get out of this? Well, we get a 1 over 2k out of this. This turns to positive sign, and then we've got ourselves another 1/2 here. Nope, we don't need the other 1/2. We already factored that out. So we've got ourselves plus 1 over 2k times the sine of 2kx. And then this is evaluated from 0 to lambda. There we go. So what can we do with this? We evaluate it, right? That's it. Well, the zeros give us 0. The sign of 0 is 0. X being 0 is 0. So we've only got to worry about the lambdas here. So we can write then that the kinetic energy of one wavelength is equal to 1/4 mu a squared omega squared multiplied by a lambda there plus a 1/2k times the sine of 2k times the lambda. So what is this? What is the sine of 2k lambda? Well, let's put that up there. Move this all down. Let's see what that is. Sine of 2k times lambda is equal to what? Well, what's k? K is the wave number, which is 2 pi divided by lambda, right? So we've got 2 times 2 pi times lambda divided by lambda. So the sine of 2 times 2 pi times lambda divided by lambda. So there's k right there. And what happens? Well, that cancels out with that. And we've got that that is then equal to the sine of 4 pi. What's the sine of 4 pi? That's right, that is equal to 0. That term does nothing for us. It doesn't matter whether it's plus or minus. But anyways, it's plus. Anyways, we've got ourselves, this term vanishes over our limits of integration. And that's it. What do we get? We get the kinetic energy of one wavelength, or housed within one wavelength, is equal to 1/4 mu a squared omega squared times lambda. Pretty cool, yeah? There we go. So what can we do with this? Well, that's the kinetic energy of one wavelength. And if we think about it, if we're treating these little mass elements like simple harmonic oscillators and talking about the kinetic energy versus the potential energy, well, we're spreading this out over one cycle where every possibility is happening. So what do we get? Well, we should have a conservative system, right? If we're treating it like a simple harmonic oscillator, restoring force and such things. So yeah, we should have a conservative system. Thus, the total potential energy plus the total kinetic energy at any given moment in time should be the total energy, being one full wavelength or whatever segment you want to look at. So there we go. We can add up the kinetic energy of one wavelength and potential energy of one wavelength to have the total energy of one wavelength. And furthermore, there should be a balancing, right? Sometimes we have the maximal kinetic energy and no potential energy, and sometimes we have the maximal potential energy and no kinetic energy. And there's this balance in between it. The energy comes, sometimes it's all potential, sometimes it's all kinetic, sometimes it's a combination. But they come overall in equal amounts. So it can be shown, but it's a little bit more, I won't say strenuous. We need a model that we utilize for the potential energy stored in the string. We basically treat it like a simple harmonic oscillator. But also, turns out that the potential energy of one full wavelength is also equal to 1/4 mu a squared omega squared lambda. So what do you end up getting with this? The total energy of one wavelength total energy in one wavelength, E sub lambda is equal to KE sub lambda plus PE sub lambda, which is 1/4 plus the 1/4 gives us the 2/4, which is the 1/2, which is 1/2 mu a squared omega squared times lambda. So there's the total energy in one wavelength. What can we do with this? We can talk about the energy transmitted per unit time. power is energy per unit time. Power transmitted is going to be the energy in one wavelength divided by the time interval over which one wavelength is produced, or the time interval over which one wavelength moves forward by a wavelength. This is kind of an average power because we're doing it over one wavelength. Average power is going to be equal to the energy of one wavelength divided by the period of the wave itself. So what do we get with this? Well, this is going to be equal to 1/2 mu a squared omega squared times lambda divided by the period. What's lambda divided by the period? Ah, that's the wave speed of the wave. Oh my gosh. Lambda divided by t is wave speed. V. So how can we write this? We can write the average power. Power transmitted by this sinusoidal traveling wave across the string is equal to 1/2 mu a squared omega squared times v. V is the wave speed, and that's it. So this could be looked at as either the power supplied to the string, because something has to be producing the oscillations, something has to be imparting energy, introducing energy to the system. This would be the energy per unit time that's delivered to the string, and assuming that this is an idealized system where there's no energy lost, no dampening in a sense, we would have no mechanical energy, I should say. No mechanical energy loss, no dampening. We'd have that power supplied is wholly transmitted through the string, and this would be the average rate of energy transmission. And there we go. So what would the units of this be? Energy transmission? Hey, we have energy per unit time. Joules per second, which is, that's right, watts. Measured in watts, assuming everything else is SI units. So that's just something of interest. Transmit energy, right? It's fantastic. Let's write the first time. Plus, and overall cosine's positive sign. Anyways, now wave bye-bye.